In parts 1 and 2 of this video series, we've looked at the radiation exchange and how it contributes to the formation of persistent weak layers. Now, in part 3, let's shift our focus to the effect of wind and precipitation. Then we'll finish with how the energy exchange varies over sloping terrain. Now, we've all blown on a cup of coffee or tea to cool it. In doing so, we're using convective heat transfer, which Mark mentioned in part 1 of this video series. This is an illustration of wind causing convection. Depending on the air temperature, wind can cool or warm the snow surface. Warm winds can melt the snow at and near the snow surface. Convective heat transfer increases with wind speed. Here's another example. In the afternoon and evening, when the sky is clear, katabatic winds can flow down big open slopes, as in this photo, bringing cool air from higher elevations and cooling the snow surface. Since convective heat transfer slows as wind speed decreases, by the time we get to calm conditions, there is no convective heat transfer. Also, conduction from the still air next to the snow surface is negligible. On some cloudy days, we have snowfall. The temperature of the falling snow is usually close to the temperature of the upper snowpack before the storm, so this usually has a weak effect on the temperature in the upper snowpack. In contrast to snowfall, rain can add a lot of heat to the upper snowpack. That is because, as we saw in part 1 of this video series, liquid water, that is rain, even at 0 degrees Celsius, contains latent heat that dry snow at 0 degrees Celsius does not. However, rain at +5 will only melt snow slightly faster than rain at 0, because the sensible heat in rain at +5 is only 15% of the latent heat in rain. When rain-wetted snow freezes, it forms a rain crust, or more generally, a melt-freeze crust, which can persist in the snowpack. Sometimes melt-freeze crusts persist for an entire winter as potential bed surfaces for slab avalanches. Also, weak layers of faceted crystals can grow above or below a melt-freeze crust, especially when those crusts are not too deep and the snow surface is cool. For a video on faceting near a melt-freeze crust, search for near crust faceting avalanche. But whoa now, we're getting away from the energy exchange at the snow surface. So far, we've been mostly talking about the energy exchange where the snow surface is level. Now let's look at how the energy exchange depends on the aspect, that is, the direction a slope faces. So it's late March on an overcast sky, and the air temperature is -5 degrees. The snow surface temperature on a steep north is -8.5, and on this gentle south-facing slope it's -7.5. So not much difference in snow surface temperature depending on the orientation to the sky, but the snow surface is cooler than the air temperature. When the sky is cloudy, the snow surface temperature is similar on different aspects because the net long-wave energy exchange is almost the same on different aspects. And as Mark mentioned, the diffuse shortwave radiation coming through the clouds does not vary much from one aspect to another. So it's late March and the sun is out. The air temperature is -3.0. The snow surface temperature on this steep shady slope is -11, and on this gentle sunny slope it's -7. So the shady slope is cooler than the sunny slope, and both the shady slope and the sunny slope are substantially cooler than the air temperature. When the sky is clear, the sunny slopes will get much more shortwave radiation and warming than shady slopes. The difference is often greater on steeper slopes, where the incidence angle on sunny slopes is closer to 90 degrees. So the amount of absorbed shortwave radiation depends on the incidence angle.
Right here on this north-facing slope is a great example of how the incident angle, or the angle at which the sun's rays hits the snow, affects how much it absorbs. It's coming in at such a shallow angle that this snow is probably reflecting almost 100% of the incoming solar radiation, and that's the factor of that incident angle. It just bounces right off.
In this infrared photo, warmer colors like yellow indicate warmer surface temperatures than magenta or blue. The snow surface is yellow on slopes that face to the right, which is west. On the afternoon of this clear day, shortwave radiation from the sun has warmed west-facing slopes more than, for example, this north-facing slope. In the early 1980s, I was caught in an avalanche because I did not adequately consider the effective aspect on snow layers. At the time, I was patrolling at the Fernie ski area, which has a lot of north and east facing slopes. In March of '83, 3 years into my patrolling career, I thought I had the local snowpack dialed. On a day off, 2 friends and I went for a ski tour on the southeast facing slopes a few kilometers from the ski area. On the way down, I triggered a large slab avalanche that released on a poorly bonded sun crust. Shortwave radiation had formed on the sun crust on the southeast facing slopes. There were very few of these in the ski area. This is a smaller avalanche that also ran on the sun crust. Aspect matters, especially in March. I should have anticipated the sun crust on the southeast slope or dug in the snowpack to see how it differed from the aspects that I was familiar with. Because of my inexperience and hubris, I was caught in an avalanche that could have killed me. I want to pick up on Mark's point about long-wave radiation from trees and relate it to terrain features. In this infrared image of a tree, we see that long-wave radiation from the tree has warmed the nearby snow surface. Similarly, the rocks and snow on this cliff are emitting long-wave radiation and warming the nearby snow surface at the base of the cliff. Now, from the perspective of the snow surface, the more view of the sky a point on the snow surface has, the more it will cool by outgoing long-wave radiation, especially to a clear sky. So if my head has this much sky view, it will cool much more rapidly than if it only has this much sky view. Also, there is more sky view and more surface cooling in the middle of a forest opening than near the trees at the sides of the opening. That is why surface hoar often grows bigger in the middle of a forest opening than at the sides. In this photo, the slope with a mostly clear view of the sky will tend to have faster radiant cooling than this slope, which has more of its sky view obstructed by the steep, cliffy slope. But you're probably thinking, whoa, shady slopes are typically cooler during clear weather. Yes, this is true, because the sunny slope receives more shortwave radiation and warms up during the day than the shady slope. So the snow surface on the shady slope is often cooler. After 1 or more clear nights, near-surface faceting and sometimes surface hoar are more likely on the shady slopes, typically on slopes that face northwest through northeast. In general, wind can warm or cool the snow surface on windward slopes more than on leeward slopes, that is, slopes that are downwind. That is because on lee slopes, the wind speed near the snow surface is usually lower. Wind can affect the formation of persistent weak layers. For example, wind can inhibit surface hoar formation. However, at the smaller scale of terrain features, the wind effect is very complex. In complex terrain, I no longer try to anticipate where a persistent layer is and is not buried. I assume it is buried on snow slopes, large or small, regardless of the aspect. Rain usually has a similar effect on slopes with different aspects. However, when there is rain with wind, the windward slopes can get more rain and receive more heat energy than the leeward slopes. Since falling snow is usually about the same temperature as the upper snowpack, uneven distribution of the snow on a windy day usually only has a weak effect on the temperature of the uppermost snowpack. When the sky is cloudy and there's little wind, the net energy exchange and the snow surface temperature are usually similar in different aspects. This is true whether or not it's raining or snowing. During the day, when the sky is mostly clear, sunny slopes are warmer because there is more incoming shortwave. During the night, slopes with a large view of the sky will emit long-wave radiation similarly. However, the snow surface on shady slopes often reaches cooler temperatures because they receive less shortwave during the day. Where the wind affects the snow surface, it can, depending on its temperature, warm or cool windward slopes more than leeward slopes. Okay, the energy exchange at the snow surface is complex, and especially complex when sloping terrain is considered. The following energy exchange processes are the big guns. Under the right conditions, they can have a strong effect on the snow surface temperature and the energy exchange at the snow surface. Incoming shortwave, outgoing longwave, rain, and wind. Considering these effects before we enter snow slopes can give us the big picture of some important snowpack layers and their possible variability over terrain. Thanks for watching, and let us know what you think of this 3-part video series.